We've all been misled by Musk. Every time I see footage of Starship, I instinctively feel this is the pinnacle of human engineering, like it's about to shoot into the cosmos any second. But here's the thing, that footage can easily trick you because if you strip away the shiny shell and the grandeur, and just look at the math, you'll see this isn't a clean victory. It's more like a really bad deal. In other words, for every bit of altitude the rocket gains, for every bit of speed it picks up, it has to trade away more mass. Now think about it. Doesn't that math start to feel off? So, this isn't just about engine power or air resistance. It's more like negotiating with a fundamental physical limit, and this limit shows no mercy. Back in 1903, a Russian schoolteacher named Tsiolkovsky derived an equation that would later define the entire space age. On paper the formula is simple, even elegant, but in reality it's brutally harsh. Because it states plainly, how much a spacecraft can change its velocity, how far it can go, depends mainly on two things. First, how fast you can shoot exhaust out the back. Second, how heavy you are at liftoff versus how light you are at the end. When you hear these two conditions, doesn't it feel like you're already being taxed? This is the rocket equation. To a layperson it looks like a travel guide, but to an engineer it reads like a verdict. Because it tells you up front, if you want to go far, you have to pay the price within these two variables, and the price gets steeper later on. So where does this steep price come from? Let's start with how our intuition gets fooled. Driving a car on Earth is linear thinking. To go farther you add more fuel. To go twice as far you add twice the fuel. Because the fuel's weight is nothing compared to the car, so it never feels like things will spiral. But rockets are different. Rockets aren't linear, they are exponential. This is where the trap snaps shut. To lift a rocket off the ground you need fuel, but the fuel itself has weight. So to carry more fuel, you first have to get heavier. But getting heavier means you need even more fuel to lift that extra weight. So the more you want to accelerate, the more weight you have to carry first. Can you feel it now? It's becoming a deeper and deeper hole you dig for yourself. In other words, a rocket doesn't just carry fuel to fly, it carries fuel to lift the rest of the fuel. Your burden doubles before you even start the real work. Isn't that a scary thought? If that's still abstract, picture this. You're trekking across a desert. You need water to survive. Water is heavy, so the more you carry, the harder you walk. The harder you walk, the more you drink. The more you drink, the more water you must carry from the start. So wanting to walk just a few extra miles makes your backpack balloon ridiculously. The rocket equation is that same logic, just scaled up to an engineering nightmare. That's why it forces us to build beasts just to put a tiny payload into orbit. Think about the rockets you've seen. Aren't they all absurdly oversized? That's not an aesthetic choice, it's forced by the ledger. Take the Saturn V, the monster that took humans to the moon. At a glance it looks like a complete vehicle, but if you look at its mass structure, it's more like a flying fuel tank. Over 85% of its total mass was propellant. Which means, the astronauts, the capsule, the valuable stuff, was just a tiny speck on top. Picture this, a tiny purpose sitting atop a mountain of fuel. Does that make sense? But it's the only way. And what's more critical, we're not starting on a flat runway, we're climbing out of Earth's gravity well. Imagine the gravity well as a deep pit. You're at the bottom trying to climb out. It's not about willpower or slogans. You need enough speed, about 11 kilometers per second, to truly escape. So the question is, how do you get that speed? You burn more fuel. And that's when the equation tightens its grip. Because the closer you get to that threshold, the more mass you need for every tiny bit of extra speed. The result is we can break through the atmosphere. We can reach orbit, but that doesn't mean we can easily venture into deep space. It's more like, you've just crawled to the rim of the pit and looked up, only to see a much longer road ahead, but you're already crushed by your backpack. So many people misunderstand one thing. They equate reaching orbit with conquering space. But the math delivers a colder truth. We are trapped by the limits of combustion. The moment you see a launch, the roar, the pillar of fire, the ground shaking for miles, it's powerful, sure. But that energy comes from chemical bonds. We recombine oxygen and hydrogen to release heat and blast hot gas out a nozzle. It's strong enough on an earthly scale, but on the cosmic ledger, chemical propulsion is frustratingly weak, because it hits a hard ceiling called the specific impulse limit. No matter how much you optimize, that ceiling is right there. Why is there a ceiling? The key is exhaust velocity. The rocket equation doesn't care how much you throw out, but how fast you throw it. The faster you throw, the more value you get from the same mass of fuel. Imagine standing on a skateboard, holding a bunch of heavy balls. You throw a ball backward and you glide forward a bit. A chemical rocket is essentially throwing such heavy balls. The mass it throws is large, but the speed isn't that high. It throws heavy but not fast. So here's the problem: if the exhaust isn't fast enough to gain the same speed, you have to throw out more mass. But before you can throw it out, you have to lift all that mass first. And the result? The exponential trap returns. You get heavier, which demands more fuel, which you can barely lift. That's why we use specific impulse to measure engine efficiency. The harsh reality is, our best liquid hydrogen, liquid oxygen rockets top out around 450 seconds of specific impulse. This isn't something you can double by trying harder. It's the hard limit of chemical bond energy density. You can't bypass it or negotiate. And as distances grow, the consequences are sobering. To reach low Earth orbit, you already need a rocket that's roughly 90% fuel, with only a tiny sliver left for structure, engines and payload. But if you aim for Mars, you need more speed. More speed demands more fuel. But more fuel makes you heavier, which then demands even more fuel. That curve acts like a merciless gear ratio, where the price gets steeper and steeper. Do you ever feel like you aren't designing the rocket? The equation is forcing you to design it its way. So what do? We cheat, we stage the rocket. Burn one stage, then jettison the empty tanks and engines, shed the dead weight, reset the math, and let the smaller remaining rocket keep accelerating. It works. We reached the moon, largely because of this trick. But staging also admits something. It's a necessary compromise, not a universal path. Because you have to burn your ship to leave port. How do you establish trade routes like that? How do you make spaceflight routine? This explains why we could land on the moon, but struggle to turn launch into daily transportation. Even more critically, the exponential trap puts interstellar travel nearly out of reach. If you wanted to reach our nearest stellar neighbor, Alpha Centauri, within a human lifetime using chemical propulsion, the fuel requirement becomes absurd, not just difficult, but fundamentally unsolvable. The curve would go vertical. So doesn't it feel like this is the true great filter for propulsion? Look at our current deep space probes, and you'll see this limitation. We don't fly them directly to their targets. We play a game of cosmic billiards, stealing momentum from planets, a gravity assist from Venus, another from Earth, then slingshot to Jupiter. The trajectory is elegant but also slow, measured in years. We're essentially giving a small initial push because our chemical engines can't provide sustained thrust all the way. So, if humanity truly wants to become a spacefaring civilization, to escape the risk of having all our eggs in one planetary basket, we can't keep relying on this slow, heavy approach. We must stop throwing heavy balls and start shooting bullets. We need a new physics of thrust. How do we break free from the rocket equation's tyranny? The answer is to change a variable. We can't easily make spacecraft mass vanish, so the practical path is to raise the exhaust velocity. In other words, stop relying solely on chemical bond energy. We need to tap nuclear power or use electromagnetic force to accelerate expelled particles much faster. Step 1 is nuclear thermal propulsion. We ditch the heavy liquid oxygen tanks and abandon combustion. We put a nuclear reactor in space, pump liquid hydrogen through the core, and use fission's extreme heat to superheat the hydrogen, shooting it out at high speed. Hydrogen atoms are light, so they accelerate more easily. With higher exhaust velocity, efficiency improves dramatically. A trip to Mars could drop from 9 months of drifting to a sprint of about 3 months. But if you truly want a solar system highway, nuclear thermal isn't enough. That's where electric propulsion or thrusters come in. An ion engine uses electricity to ionize gas, then uses electromagnetic fields to fling the ions out at tremendous speed. Velocities can approach 90,000 miles per hour. The thrust is tiny, too weak to lift a rocket from Earth. But once in space, the environment changes. No air resistance, no need to fight the gravity well from the ground. That tiny thrust, if sustained, becomes incredibly powerful. A chemical rocket burns for minutes and stops. An ion engine can thrust for months, even years. It's not fierce, but it doesn't quit. Speed piles up bit by bit. This is how we skirt the mass limit. We trade energy for mass. You carry a powerful energy source, like a nuclear reactor or vast solar arrays, and use a tiny amount of expelled mass, but shoot it out extremely fast, still gaining momentum. The rocket equation still holds, momentum is still conserved, but the terms of the deal change. They change in our favor. We are no longer trapped by the weight of our own fuel. And this change is civilization level. Once we master high exhaust velocity propulsion, the solar system transforms from a vast impassable desert into a chain of reachable islands. Mars, the asteroid belt, Jupiter's moons, stop being death-defying stunts for a select few and become sites for industry and infrastructure, even places for sustained human presence. So the rocket equation, this hard filter, isn't a wall. It's more like a test. It demands you first master the fundamental forces of matter and energy before it lets you leave the cradle. For the past century, we learned to crawl with chemical rockets. Now, harnessing the power of atoms and electrons, we are finally preparing to walk. The rocket equation is still written in the stars. It is the permanent law of motion in the void. It tells us the price of gravity is steep. The universe does not give up distance easily. But when we truly understand its cold logic, we also find the key to escape it. We finally see that to reach for infinity, we must first look inward to the atom itself, because the power to push back the darkness is hidden there.